Okay, this is the last video for this chapter, and we will continue the example we considered in the previous video. So in the previous video, we considered an example of overbooking, and we considered that there are 20 seats, but the airline company accepted 22 reservations. Now we are going to and then the probability of overbooking problem is nearly 34%. That's what we calculated. Here, I want you to study what happens if you reduce the number of reservations to 21. So the airline company may think 34% is too much. So the probability of overbooking problem is too high. So let's reduce the size of the overbooking. So still the company is still overbooking, but accept overbooked, but like like reduce the number of overbooking to 1. So now accepts 21 reservations for 20 seats. In this case, do it by yourself. You find the parameters for the binomial distribution and then find the probability of overbooking. More than 20 passengers want to take the flight. So follow the same steps as before and see how much this reduces the probability of the problem. So pause the video now and I will show you how to do this. So first, you have to find the parameters, and P is 0.9. That does not change. But the parameter N is now 21 because the airline company sold 21 reservations. So the maximum number of passengers maximum number of passengers is 21. And then we are interested in the probability that y is strictly greater than 20. I said that the probability defined by an inequality is not directly solvable for the binomial distribution. And then you can simply consider this equality because there is only one outcome strictly greater than 20. Because once the n is now 21, 21 is the only possible value, strictly greater than 20. So I put 21 here, and then just apply the formula. 21 choose 21, and 0.9 happens 21 times. So if you calculate this, it will give you about 10.942%. So what's interesting here is when you reduce the sample, the number of reservations from 22 to 21, you may think it's like a reduction by only 1 out of 22, or you may think it's a reduction by half, like the overbooking has decreased by half. Or either way, the movement of the probability is quite cannot be directly inferred from those numbers. So the probabilities, the binomial distribution probabilities are not that clear like from those given numbers. So you have to really calculate the probability and see what's the result. It cannot be done like intuitively. So here, just one change by 1 reduces the probability less than 1/3, right? All right, so the small change in the parameter could have a huge impact on this probability. So the binomial distribution is quite unintuitive. It's not easy to understand what's going on. It's like a black box. So we know the formula, but it's hard to understand how it behaves and how it would change when you change something. So That's why I spent like a lot of time to explain binomial distribution. Okay, this is the last example of this chapter, quality inspection. So suppose that now I'm going to consider a firm that manufactures batteries, like smartphone batteries, for example. But the problem is that some batteries may be defective, and I'll assume that the probability of a battery defect is 5%. So 5% of batteries are defective. And now you are the manager of the smartphone manufacturing factory. So you receives the batteries from that manufacturer. So you are using the batteries for your final product. So, and you are the quality control manager. That is, you have to screen the defective batteries like from the shipment. So what you are going to do here is, say you receive a number of batteries, a huge number of batteries from the supplier, but you cannot check all of them. So you randomly choose 10 batteries, say, randomly choose 10 batteries and inspect only 10 batteries. And you are going to reject you are going to accept the shipment only if 2 or fewer batteries are defective. So you may think it's generous, but like of course the numbers are like just made up numbers for simplicity. So now, then I'm going to define y, the random variable y, as the number of non-defective batteries from the inspection of 10 random batteries. So you choose random 10 batteries, and then the number of defective ones, the number of non-defective batteries from those randomly chosen ones is y. So, and then we know it is another binomial distribution, binomial random variable. Then, like, think about this. What is the probability that the battery shipment is rejected? So you like screen out, you don't accept the batteries as a quality manager. So this step is like to formulate the story, the situation into statistical formulation, statistical notation. So remember, you accept only if 2 or fewer batteries are defective. That means, but we are counting non-defective batteries. So you have to change this into non-defective batteries. That means equivalently, you accept only if 8 or more batteries are non-defective, right? So they are equivalent. You are here in this sentence, we are counting defective batteries, 2 or fewer, but we, in our formulation, statistical formulation, we are counting non-defective batteries. So it has to be 8 or more non-defective batteries. But also, on the other hand, we are looking at rejection. So if you replace the accept with rejection, then this means you reject the batteries if the non-defective batteries are 7 or fewer, right? So if there are 3 or more batteries are defective, then you are going to reject. That means if 7 or fewer batteries are non-defective, you are going to reject. So, you know, we are changing the side, like whether we are counting defective ones or non-defective ones. And also we have to think about when we accept or when we reject. They are just, they're flip sides. They complement each other. Just so it's your kind of IQ test. So like brain teaser. Anyhow, then as I said, the answer is E. So you reject if the number of non-defective batteries are 7 or fewer, right? And then the next step, so we just defined what we want to calculate. This is the probability we would like to calculate. And then the next one we need to do is to find the parameter values. In this case, you are randomly choosing 10 batteries and count how many are non-defective. So the maximum non-defective number batteries, the maximum number of non-defective batteries is 10. That is one of the parameters, n equals to 10. And the success is non-defective batteries. Success is non-defective batteries. So the parameter p is its probability, which is 95%, because defective rate is 5%. So the probability of non-defective batteries is 95%. And then how do you calculate that? So now it's a probability defined by inequality. But this is not easy to handle because there are eight possible outcomes. So if you break them down into equalities, you need to calculate 8 different probabilities, which is not good. So here is another trick. Instead of calculating 7 or fewer, I would calculate 8 or more, and then subtract that from 100%. So this is the probability of accepting the batteries, right? And then if you know the probability of accepting batteries, then automatically you can calculate the probability of rejecting them. So, and because the probability of accepting is easier to calculate, I'm going to take this way. And y greater than or equal to 8 includes only 3 probabilities. So calculate them. It is easier to calculate 3 probabilities than 8. So that's how we we are going to calculate the final probability of rejecting the batteries. So calculate 3 of them and subtract from 100%. That's another way to handle probability defined by inequality. So it was a long chapter, and in the next chapter we are going to start another statistical model, normal distribution. And so it will be a different topic. So have a nice week and see you next week. See you later. Bye.